Alright, back into section 11.3. So looking at the next topic, I'm estimating the sum of a series. So we're looking at using things like the integral test to be able to help us determine approximately what the sum of a series is. So not just convergence or divergence. So once we determine a series is convergent, we can approximate the sum S of the series using the partial sums S sub n. To figure out how accurate this approximation is, we use the remainder. Okay. So this is denoted R sub n, so big R sub n. So this is S minus S sub n. So when we say S minus S sub n, so remember S is the actual sum, whatever it is. S sub n is the approximation we get using the partial sums. So the remainder is just telling us how close was our approximation to the actual sum, okay, by subtracting one from the other. Okay, so the remainder, R sub n, is also called the error. So this is the error made when S sub n, when the partial sums are used to approximate the actual sum S. Okay. So suppose f of k equals a sub k, where f is a continuous positive decreasing function for x greater than or equal to n, and the series is convergent. If the remainder is the sum minus the partial sums, okay, then we have the following relationship. So we have the integral from n plus 1 to infinity of f of x dx. That is less than or equal to R sub n, which is less than or equal to the integral from n to infinity of f of x dx. Okay, so basically, if we're trying to visualize what's happening here, we have our curve doing something like this, and here is n, here is n plus 1. We're saying that the value of the remainder is going to be somewhere between here and here. Okay, so somewhere in there we get our remainder value. Okay, so it's kind of telling us how close did we come to getting the actual sum. Okay, so let's look at this example. So this is the one we're going to be using for the last couple here. So use the sum of the first 10 terms of the series 1 over n cubed, approximate the sum of the series, and estimate the error involved in this approximation, and then it asks how many terms are required to ensure that the sum is accurate within 0.0005. Okay, so first thing, before we even do any of this, we're going to need to get that improper integral if we're going to solve these problems. So let's get that first before we do either A or B. So we'll need the integral from n to infinity of 1 over x cubed dx. Okay, so this is limit as t approaches infinity of the integral from n to t. But let me go ahead and just take the antiderivative right now. So that's negative 1 over 2x squared from n to t. So that is the limit as t approaches infinity of negative 1 over 2t squared plus 1 over 2n squared. And as t goes to infinity, this term goes to 0, and this term is unaffected because it has no t's in it. So that first term turns into a 0, so this is 1 over 2n squared. Okay, so the value of this improper integral is 1 over 2n squared for whatever the value of n is. Okay, so that's going to be helpful when we're running these calculations here in just a minute. Okay, so let's look at part A. So approximate the sum of the series. So this is something we can do just using, we could do this by hand if we wanted to, but we'll just use technology for this. So the series of 1 over n cubed. This is going to be approximately, right, the 10th partial sum. Now, obviously, if you want a better approximation, you should use a larger partial sum, right? Because the more terms you include there, the closer you're going to get to the actual value. But this one just asks for 10. So that's going to be, right, 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed up to 1 over 10 cubed. Okay, and this, if we plug and chug that, is approximately 1.1975. So now the question is, how close is that? Right? How accurate is that value? And what is the error involved in this approximation? So the remainder, right, that error, that's going to be R10. We know that this is less than or equal to the integral from n to infinity. In this case, n is 10 to infinity of 1 over x cubed dx, which we found, again, up here. That's 1 over 2n squared. So that's 1 over 2 times 10 squared. So that's 1 over 200. So that tells us that for this estimate, okay, this approximation of 1.1975, the error is at most 1 over 200, which as a decimal is 0.005. So our error is at most 0.005. So depending on how accurate you need to be, you could say, oh, that's great, that's close enough for me. Or you say, actually, I need to be a little more accurate than that, so let's use more terms. Okay, and this kind of leads into part B, because part B says how many terms are required to ensure that the sum is accurate within 0.0005. Okay, so maybe you're saying, well, I need to be, this accurate within 0.0005. Then in that case, okay, how many terms do I have to do? Well, we can figure that out right now. So, to be within, so let me just type this here. So to be within 0.0005, we need to find n such that Rn, that remainder, that error, is less than or equal to 0.0005. Okay, so we need to find that n value that makes the remainder smaller than that number. Okay, so let's use what we know. So we know that the remainder is less than or equal to the integral from n to infinity, right, of 1 over x cubed dx, which is 1 over 2n squared. So that's what we know. What we want is for this value of the remainder here, right, which we're saying is less than or equal to 1 over 2n squared, we want that to be less than 0.0005. Okay, and now that we have this relationship here, right, which is what we want, we can solve this for n. Solve the inequality for n, and that's going to tell us how many terms we need. So we go ahead and multiply, right, the 2n squared across. So that's going to be 1 less than 0.001 n squared right? Multiply 0.0005 by 2. Divide by that 0.001, so we get n squared is greater than 1 over 0.000, oops, excuse me, one too many zeros, 0.001. 1 over 0.001 is 1,000, okay, because that's 0.001 is just 1 over 1,000. So this is 1 over 1 over 1,000. So taking that reciprocal, that's just 1,000. So this gives us n is greater than the square root of 1,000. And the square root of 1,000, just to put that into more clear perspective, that is 31.6. So we need n to be greater than 31.6 in order to get this level of accuracy, to be within 0.0005. Okay, so we need n to be greater than 31.6, so n needs to be a whole number, so we'll just pick the next whole number, so that would be 32. So we need 32 terms to ensure accuracy within, oops, sorry, 0.005 units there. All right. So we are going to need 32 terms to get that level of accuracy. So the 32nd partial sum is what we would need. Okay. So now, going based off of this, let me just go back up to the top here. So going based off of this relationship here, the fact that the remainder is between those two integrals, if we just go ahead and add the partial sum to all sides of that inequality, it's going to give us the actual value of the sum in the middle. Right? Because if we take, right, the partial sum plus the remainder, that is the whole thing. Right? That's the entire sum s. So this is going to give us s is between s sub n plus this lower integral, n plus 1 to infinity of f of x dx, and s is less than or equal to s sub n plus the integral from n to infinity of f of x dx. Okay, now we can use this to determine a much better bounding, right? Because we have it's greater than this number, it's less than this number. We can bound s. We can find a better approximation of what the actual sum is going to be. Okay? So use this inequality, so they're talking about this inequality up here, with n equals 10 to estimate the sum of the series 1 over n cubed. So the same series. So we're going to use n equals 10 in here, so let me keep that on the screen. So we're going to have s sub 10 plus the integral from n plus 1, so 11 to infinity of 1 over x cubed dx less than or equal to the actual sum s less than or equal to s sub 10 plus the integral from 10 to infinity of 1 over x cubed dx. All right. So we already know how to solve this integral, so we've already done it. So let's just make a note of that. So we know the integral from n to infinity of 1 over x cubed dx equals 1 over 2n squared. So let's plug that in. So we get s sub 10 plus 1 over 2 times 10 squared, or excuse me, that's 11 squared. I mixed my numbers up there. There we go. Less than or equal to s, less than or equal to s sub 10 plus 1 over 2 times 10 squared. Okay, And then we found an approximation for S sub 10 in the last example. I'm going to take it a couple decimal places further this time, just for the sake of even more accuracy. But we get 1.197532. So if we add this value onto this side and to this side, okay, and then obviously solve those fractions as well, this is going to give us a bounding. So on the lower bound we have 1.201664 is less than or equal to S, which is less than or equal to the upper bound of 1.202532. Okay, so this gives us kind of a lower and upper bound. So to actually estimate the value of S, that sum, we can go ahead and take the midpoint of this interval and use that as our approximation. That way, the error, the only potential error, is going to be half of this interval, right? Because if I have the interval from here to here, and I pick the middle value, then my error must be at most half of that interval on either side. Okay, so let's write that out. So use the midpoint of the interval for our approximation of S, and the error is at most half the interval. Okay, so this gives us the sum from 1 to infinity of 1 over n cubed is approximately the midpoint of that interval, so 1.2021, with error less than half the interval, so 0.0005 is half that interval. So this gave us not only whether it was convergent or divergent, but this one actually gave us a good approximation for the sum and told us what the error was. Now notice the error here, 0.0005, that is the same amount of error we had in the previous example using 32 terms. But here, we only had to use 10. So that gives you just the strength of this particular method. So let's just make a note of that. So notice this gave us, a good approximation within 0.0005 using only 10 terms instead of the previous one told us 32, right, from the previous example. That one told us we're going to need 32 terms to get this accurate, and using this method instead,